Hello, my name is Robert Smith, and I'm with New River Community College. And today we are looking at the assigning of unpaired spins in a coordination complex based on ligand field theory. And essentially, what that is classically you were taught that 5D electrons will appear, they'll file in according to Hund's rules, singly and then in parallel, just like in the order that I'm filling them in now. But in reality, what we find is when we add ligands to these metal atoms, that this does not hold. That the 5D electrons are the 5D orbitals specifically are non-degenerate, which means that they are not of the same energy. So what we want to look at is what kind of energy levels they do have, and what happens is that for octahedral complexes, which is what we're dealing with in this class, you'll have this degeneracy breaking. And some of the 5D electrons, such as dxy, dyz, and dzx, as well as will be at one level at a lower energy level, while dz squared and d x squared minus y squared will be at a slightly higher energy level. And you would want to necessarily use Hund's rule, just as you would with a completely degenerate case. But depending on the spectrochemical series and the strength of the ligand, the so-called strength of the ligand, will determine whether this is whether there's a strong field ligand or a weak field ligand. And a strong field ligand will have a high spin state, and a weak field ligand will have a low spin state. So based on your spectrochemical series, we can assign our unpaired electrons just using this formula here. And to do so, we simply look at the ligand, which in this case is carbon monoxide. Carbon monoxide is a strong field ligand, which means that it has low spin. And when it has low spin, you simply keep all the species in your lower orbitals. So whether this was high or low spin, you would have these 3 electrons that would be spin up, and they would be in those 3 orbitals. But there are 4 electrons associated with chromium 2+. So we need to decide what to do with that 4th electron. And because carbon monoxide is a low spin, is a strong field ligand, which yields to a low spin, that means that our 4th electron will actually be spin down on one of the lower orbitals and won't ever get into the upper orbital unless it's excited into that state. Conversely, water is a weak field ligand, so it has a high spin. Manganese 2+, you'd expect 5 electrons, and normally we would automatically put those first 3 in spin up on the lower 3 orbitals. But what to do with the other 2 is based on whether it's a high spin or low spin state, whether it's a weak field ligand or a strong field ligand. Water being a weak field ligand means it's a high spin state, which means those other 2 electrons go up here in the dz squared and dx squared minus y squared orbitals. So that's essentially the short version of how you assign unpaired spins. So for the first one, for the hexacarbonyl chromium 2, you would have 2 unpaired spins. So this one would be a 2. And that's because we have an unpaired spin here and an unpaired spin here. For hexaqua manganese 2, you would have 5 unpaired spins because each of the orbitals only has 1 electron. You don't have any doubling up like you did in chromium. And again, the reason why there's 4 electrons for chromium is chromium 2+ has 4 electrons, and we treat even the s electrons, the s orbital electrons are treated like d electrons for the case of ligand field theory. And also we have 5 electrons on the second case because manganese 2 plus has in effect 5 electrons in its valence shell.